Welcome, ladies and gentlemen. Let's go ahead and take a look at these series and determine whether or not they converge or diverge. And we have a couple reasons, right, why a series might diverge. And so let's go ahead and see if any of those show up. Firstly, if a series is geometric with our ratio r less than 1, it's guaranteed to converge. Not only do we know it converges, but we can also figure out to what value it converges using our geometric formula. And so if the first one, right, looks to me like a geometric series with r equals 2/3, 2/3 is less than 1, therefore this must converge. And so this is a geometric series with r equals 2/3 is less than 1, therefore converges. Not only does it converge, we can also calculate what it converges to. All right, so not only does the series converge, but we can figure out what it converges to. Let's plug into our formula. It must converge to a over 1 minus r, where a is the value of my first term, and r is my ratio. So I need to go and figure out what my first term is. It's not necessarily 5, right? It's not necessarily 5. However, when I plug in 1 and evaluate the first term given my nth rule, it looks like 1 in for n minus 1 is 0. 2/3 to the 0 is 1 times 5 is 5. So it looks like the first term is 5, yes? So a is 5, which means that this must converge to 5 over 1 minus r. We already decided that r was 2/3. So we can do a little bit of algebra. And we get 5 over 1 minus 2/3 is 1/3. And dividing by a fraction is the same as multiplying by the reciprocal. So it looks like I'm getting 15. Raise your hand if you get 15. Anybody else get 15? Yes! Nice. All right, so let's go ahead and take a look at the second one. Firstly, as you look at our definition for the nth term, in the second one, does that appear to be geometric? No, we don't see this constant ratio raised to, right, the nth power. Instead, I see a rational expression, n over n plus 5. And so if I were to list the first several terms in this, because it's true that this does equal, right, this does equal the sum of an infinite number of terms, each of which is given by my generalized rule. So when n equals 1 looks like my starting index value, 1 over 1 plus 5 is 1/6. Plus, when n equals 2, raise my index counter by 1, and I get 2 in for n is 2 over 2 plus 5 is 7, so 2/7. Plus, right, and as I continue on, 3/8, 4/9. What's happening to the term values as, right, as n gets larger and larger? What's happening to my term values? Sophia? They're increasing, right? And we know that a series only converges if what's true about the term values? Well, they must approach 0, right? Now, just the fact that the term values approach 0 doesn't mean that a series converges. It's just a necessary prerequisite. If the term values don't approach 0, then there's no way that the series, the sum of all those terms, will be finite. And so the fact that these term values are increasing as n gets larger is indicative that the series diverges. Now we can formalize that pretty easily just by doing the limit of the nth term, right? And we call this informally the nth term test. But if we just consider the limit as n goes to infinity of my generalized rule, n over n plus 5, we saw a technique algebraically where we could simply divide every term by the largest power of n that appears and read it algebraically without having to get into L'Hopital's rule or anything like that, and try again. I'm getting the limit as n goes to infinity of n times 1 over n is 1 over n times 1 over n is 1 plus 5 over n. And now I can evaluate this as n goes to infinity. 5 over n goes to 0, and I'm left with the constant, which is 1. Since the limit of the nth term is 1, which does not equal 0, the series diverges. So we could call it the series diverges by the nth term test.
on like a test? Do you have to do that to show our work, or just say diverges?
Don't know yet. For now, I would say yes, show that. You should be able to show that algebraically. Don't know yet in terms of point values because we're a long ways out. Series diverges by nth term test. And I think a squiggle underline, a little emphasis for diverges in order. Okay, so then who else got diverges for number 2? Over there for diverges? Hey, you guys are 2 for 2. That's good. All right, let's take a look at number 3. So now I try to change the rules, right, so that we had to do a little manipulation perhaps before we could tell whether or not it converges or diverges. And so instead of going and starting listing the terms right now, instead what I would do is try to rewrite the rule to see if I can make it look, right, like number 1. So let's go ahead and see with my properties of exponents, this is equivalent to the sum from n equals 0 to infinity of, I'm going to break up that 4 to the n plus 1, right, is 4 to the first times 4 to the n. Isn't that 4 to the n plus 1? Right, we've got one more multiplier of 4, so that's 4 to the first times 4 to the n. By doing that, I've created the same exponent on my 4 and my 5. Does everybody see that? So that I can rewrite that as 4/5 to the n. And that's helpful because now we'll be able to determine what kind of series this is. So n equals 0 to infinity of, group that 4 out front, and less u. So you see, we've rewritten my original so that now, yes, number 1, number 3, number 1, number 3, they're like the same. So what do? We say, oh, this looks like a geometric series with r equals 4/5 is less than 1. So the series converges to first term over 1 minus r. So let's do it. So we'll say geometric series with r equals 4/5. So converge to, and it looks like n equals 0 is my first, right, my first term. When n equals 0, 4 to the 0 plus 1 is 4. Over 5 to the 0 is 1, so I'm getting 4. Are you getting 4 for your first term? So a equals 4 over 1 minus 4/5. And I didn't mean algebra, just a little evaluation here. So 4 over 1 minus 4/5 is 1/5. Is that right? 1 minus 4/5 is 1/5. And 4 divided by 1/5 is the same as 4 times 5, so we're getting 20. So raise your hand if you had 20. Anybody else at 20? Well, you guys got stuck on the nth row? Or you're okay? All right, so good. We're going to have an opportunity to practice with this generalized form and manipulating with those exponent properties, okay, so that we're able to make it look. Let's do the same thing for number 4. So as I look at number 4, right now I can't tell whether or not it converges or diverges. Let's go ahead and see if we can't use our properties of exponents to rewrite the nth term and see what it looks like. So I'm going to go ahead and keep my summation notation. This time starts at 1 to infinity. But let's rewrite that. I know that negative exponents don't mean negative answer. Negative exponents mean reciprocal. And so I'm going to grab onto that 3 to the negative n and rewrite that on the bottom as 3 to the positive n. Yes? Meanwhile, we'll go ahead and use the same technique we did in number 3 to rewrite that power 8 to the, right, 8 to the n plus 1. And rewrite it as 8 times 8 to the n. So there's our 8 times our 8 to the n plus 1. And that's all over 3 to the n. Now this is looking, right? Now this is looking like we'll be able to tell. So this is Gardner. So it looks like n equals 1 to infinity of 8 times 8/3 to the n. And now does it look like number 1? Now it looks like number 3, so now we can tell. So does this series converge or diverge? Riley?
It diverges.
Why does it diverge?
Because r is greater than 1.
Absolutely. So this is geometric series with r equals 8/3 is greater than 1, therefore diverges. Good. Diverges. Awesome, Blossom. Cool. One to go? All right. So let's go ahead and use the same techniques we've been employing now and see if we can handle number 5. Trying to make it, let's see, similar but a little bit different. What about the -1? All right, what is that -1 in that exponent? And -1, well, that would be like -3 to the -1 times -3 to the n. And we know a negative exponent can be rewritten as a positive exponent if I take the reciprocal. And so what I'm going to do is break this up and grab one of those -3's and put it down below. What? Well, this is going to be n equals 1 to infinity of -3 to the n over -3 to the first times 4 to the n. So by rewriting it like that, we do see we have the -3 and then the 4 on bottom are both to the n power, so I could write that as -3/4 to the n, yes? And then I still have that -3 on bottom, so let's see what that does. So it looks like, I'm going to go too many steps at once here, I don't want to mess up. So it looks like I've got -1/3, there's that -3 to the first on bottom, yes, times, and now I've got -3/4 in parentheses, yes, okay, so what do you think? Converge or diverge? So what do you think for this one? Sophia? Converge, yeah, we've got a geometric series. Can r be negative? Absolutely. We just need the absolute value of r to be less than 1. So, yes, this is a geometric series with r equals -3/4, absolute value of which is less than 1. So, we're good to go. We'll go ahead and say that. Geometric with r equals -3/4 and the absolute value of r is less than 1, therefore converges to, oh boy, now I've got to do a little calculating. Let's figure out what our first term is. So I'll go to my index. It looks like this starts when n equals 1. Oh, that's no problem. So -3 to the 1 minus 1 is 0, is 1 on top, over, for the first is just, is that 1/4 for your A? Okay, so 1/4 over, oh boy, goodness, over 1 minus r, and my r was -3/4, yes? So 1 minus a negative is the same as 1 plus a positive, so I get 1/4 over, go gadget arm, 1 minus a -3/4 is 1 plus 3/4 is 7/4. And we know that's the same as multiplying by the reciprocal. So 1/4 divided by 7/4 is the same as 1/4 times 4/7. Well, that does work out nicely, doesn't it? Second favorite game, you guessed it, the cancel game, so I get 1/7. Awesome. What questions do you guys have about today's Bellwork? This is a little bit of a warm-up for some of the series representations we'll be dealing with today. We're going to let series represent functions and vice versa. So this is a big day as we transition from just dealing with numbers, numerical entries, right, with the numerical value of r fed to a variable value for r. So this is a big deal. Okay, but first let's go ahead and pause the recording and take care of our OTL and then our test back. Okay, ladies and gentlemen, so we already know, right, after one day, really all there is to know about a geometric series. If a series is geometric, as is the case of several of our Bellwork questions, we have everything we need to know about convergence versus divergence. So the geometric series, right, given by the sum from 0 to infinity of some constant a times r to the n, expanded out the first several terms were like a plus ar to the first plus ar to the second plus ar to the third dot dot dot. That converges, right, if the absolute value of r is less than 1. And its sum, we know as well, we did in our Bellwork, it's simply the first term divided by 1 minus r. If r is greater than or equal to 1, right, then the geometric series diverges, right? So we already know all there is to know, really, in terms of convergence and divergence of a geometric series. So now it's time to bring in x. We're going to consider then what happens if we let that ratio r, which has been a number up until now, a set number like 2/3, we're going to now let that be our independent variable and use series to represent functions and functions to represent series. This opens up a whole range of possibilities, because before we were letting r just be a single particular value, and now we're going to let r be an independent variable, right, which could take on multiple values, and use the function then to analyze series and vice versa. So if the sum from 0 to infinity, if we have our basic geometric series, a times r to the n, and we know if it converges to a over 1 minus r, we're going to go ahead and let our r equal x. And now we know that the series a plus ax squared plus ax cubed, which is going to be our parent power series, converges, right, if and only if x now, the absolute value of x, is less than 1. And we know what it converges to. If x, absolute value of x, the magnitude of x, is less than 1, that is, if x is in between -1 and 1, then what must this converge to? Well, my geometric series converges to a over 1 minus r, so this must converge to what? The geometric series converges to a over 1 minus r, so what must this converge to?
A over 1 minus x.
Yeah, a over 1 minus x. In fact, that's going to be the function f of x that represents our parent power series. So, well, I'll call it a because of a in this case. That's just a constant. It could be 1, it could be 3. Alright, so this is kind of a big deal. If we let r be replaced by x, we have our power series, or our infinite power series, is simply given by a over 1 minus x, which is a function, right, in its own right. By representing a series with a function and vice versa, we can access then all of our calculus tools, including differentiation, integration, and domain, right, preservations as well. Cool. So let's go ahead and graph our parent power series function f of x and the first several terms in the series that it represents on the same graph. And we're going to do this with our graphers as well. So let's go ahead and let our parent geometric function f of x, our parent power series f of x, be given by 1 over 1 minus x. We've seen how this represents the series from n equals 0 to infinity of x to the n. What would the first several terms of this power series be? Right? If we were to expand that out, what would the first several terms of that power series be? Tyler?
I'm losing 0, so x goes to 0.
Yep, which is?
1. X.
Yes,
X and 4.
absolutely. And so guys, what we're going to do is we're going to set our window here. We're going to compare these two different representations. Thank you, Tyler. We're going to compare these two representations, right, on our graphing calculator in the same viewing window. So everybody, let's go ahead and set our window to -2 to 2. And we'll go -5 to 5. And we'll go ahead and let our function f of x be 1 over quantity 1 minus x. Watch you use the parentheses. And first I'm just going to do a quick graph of that so that we see if this window is going to work. -2 to 2 and -5 to 5. Okay, so now what we're going to do is we're going to enter a second function, right? Call it, well, y sub 2. And in our second function definition, we're going to go ahead and enter the first several terms of the power series that this function is supposed to represent. What are the first several terms? Well, the first several terms are, Tyler told us, 1 plus x plus x squared plus x cubed. Love the math 3 shortcut. That's pretty sweet. I want to see what this looks like first. So I'm going to go ahead and do with my red line style. I'm just going to do 1 plus x squared plus x cubed. And I'm going to graph them in the same viewing window, right? I'm going to see what happens. So here comes. All right, so how does that red function, the first several terms of our series y sub 2, compare with the original blue? I don't know. I mean, it definitely looks similar there in the middle, but it leaves something to be desired out here, yes? All right, let's go ahead and go back to my function definition, and now let's go ahead and add another couple terms for my series. Let's do 1 plus x squared plus x cubed plus x to the 4th. Yes? All right, so let's see what that does. And how does that function do? Well, it looks like it does a little bit better. As you look at this right-hand side in particular, you see right there, it's actually closer to the blue than it is, right? It's closer to the blue than the red ones. You see that? Let's go ahead and add one more, and then we'll deal with the issue of convergence. So I'm going to go ahead and do 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. Yeah, you want more? Plus x to the 6th. Why not? I'm here. All right, so I went ahead and added 2 more terms. And now the pink line style, I'm hoping, here comes, and it sure looks to share, right, much more with the blue than all the other ones. So what's the point here? Well, I want you to consider, right, that we've only added 6 of my terms together, right? We only did the first 6 powers of x, and this is an infinite series that goes forever and ever and ever. Could you imagine adding more powers, right? In fact, by the time we get to x to the 11th here, there's virtually indistinguishable difference, right, in between our first, and it goes to an infinite number of n's. And so this power series, right, equals that function, y equals 1 over 1 minus x, and vice versa. Okay, and so what we're going to do now is determine the interval of convergence. We already know that my geometric series converges when absolute value of r is less than 1. Guess what? This then converges for all values of x, so long as absolute value of x is less than 1. And we know back from algebra that we can get rid of absolute value bars, right? By setting this into a compound inequality. That means that x must in between -1 and 1. So in interval notation, my interval of convergence is negative 1 to 1 for this parent function where r is replaced with x straight up. Now this will change, right, if my substitution for r isn't just plain Jane x. If it's 2x, for example, right, or negative 3x, then it's going to change this interval of convergence. But this is my parent function, and this is the parent interval of convergence. Would you buy that? Well, yeah, as I look at the picture, it looks like my power functions do a very good job, right? A very good job of matching when I'm in between what x values? Negative 1 and 1, but a cruddy job anywhere else. In fact, over here, right, we've got total divergence. Do you see that? This whole bottom branch, here my power functions are up here, and it's down here. And so it only holds true then if x is in between negative 1 and 1 for my parent. So that's kind of where we're headed, and that's what we're going to use for our basis. That's pretty sweet. Definitely PDF-able, Tyler. All right, so our interval convergence then, if our geometric series converges when absolute value of r is less than 1, then our power function, right, power series, I should say, n equals 0 of a x to the n converges when, I'm going to go ahead and do this one more time, you can write that down. Converges when absolute value of x is less than 1. For us, that means negative 1 is less than x is less than 1, and in interval notation, that would be on the interval negative 1. Strictly, right, strictly. Cool. So now we have the setup, right, the scheme. We've got lots of things that now we can draw on from our calculus, our regular calculus continuous functions knowledge from AB, and now apply it in the new realm of series for BC. So since power series represent functions, we can differentiate series term by term, or differentiate the function using our rules that we've already developed last year. Similarly, we can integrate series term by term, or integrate the function using our rules. And then the interval of convergence for a series is preserved through our regular calculus processes of differentiation and integration. So where does that leave us? Well, let's go ahead and practice then representing series as functions, and vice versa. We're going to let functions represent series. We'll also differentiate and integrate, and then generate a new series representation for each. So we're going to kind of cast this notion of infinite series in the backlight of what we've already developed with integration and differentiation last year in AB. So by making various substitutions for r or x, we can create series that represent a variety of different functions and vice versa, and that's exactly some of the stuff you're going to have to do in your assignment tonight. All right, so let's go ahead and practice some. State the function the given series represents, and determine its interval of convergence. The key here is being able to rewrite this in such a way that we can tell what x equals, or what r equals, right, so that we can write it as a function. All right, so let's go ahead and take a look at our first one. How could I make this look like, right, how can I make that look like a power function, something to the n, right, some quantity to the n? Well, in this first one, both of those are to the nth power, yes? So I can just use my properties of exponents and rewrite that as the sum from 0 to infinity of, and I can just rewrite that as, right, we're trying to make this look like something to the n, so that it looks like that. So it looks to me like negative 3 x. So by rewriting that as negative 3x to the n, we can perform a direct substitution to generate the function, right, represented by this series. So let's call it my new function f. Let's call that function f. There's no a multiplier out here, and so that's just 1. If I were to plug in my first term to figure out what a is, 0 in for my index becomes 1, so I just have 1 over 1 minus, and this is normally r, right, or x, but in this case we have the substitution negative 3x. So that's what we're going to put in. Grace?
Why is it not 2a?
Oh, great question. So if you were going to take 2x cubed y squared, right, and cube it, right, who gets cubed? The 2, the x cubed, or the y squared? They all do. And my means for doing it is I do each one. 2 cubed, x to the 3 cubed, 9, y to the 6. So who got it? Everybody got it. So if I can rewrite that as, right, the cubes, and then now go back the other direction, then I can rewrite it as a single one like that. The power has to match to rewrite it then as a product. So if 1 was to the n plus 1, we have to break it up and then make it so the exponent's the same, and then we can condense it as a product to the same exponent.
Okay.
So we're just going backwards. All right, what does that do for us? Well, now look, this is my function f of x, and from that substitution I can answer the things about interval of convergence. However, that looks kind of silly, and so what would we probably do? Well, we'd probably rewrite this as 1 over 1 plus 3x, or 1 over 3x plus 1. So when you look at the back of the book, yes, we've correctly found our substitution, but it's probably going to look like this. Yes? Cool. So let's go ahead and determine my interval of convergence. For that, I'm going back to the substitution that we made. We know that our regular parent power series converges for absolute value of x less than 1. However, in this case, it wasn't x, it was negative 3x. So my interval of convergence can be determined when absolute value of negative 3x is less than 1. So I figure out what my new ratio r is. And I need the magnitude of that new ratio to be less than 1 to guarantee convergence. And then I can, well, apply my property of absolute value. That's really just negative 3 times x inside. So the absolute value of negative 3 inside is the same as 3 outside. We know that this means the absolute value of x must be less than 1/3. So it looks like my interval of convergence is going to be in between negative 1/3 and positive 1/3. So in interval notation, that would be negative 1/3 to 1/3. Cool. All right, so what I want to do, I'm going to can that. What I want to do then is see how we did. Okay, so I want to see how we did one more time with the grapher, and then we're not going to check every time, but it is worthwhile for us to do a little bit of practicing here. So if I were to expand this in the first several terms, I picked on Tyler last time, you see to take it in stride. So if I were to expand this, right, what would the first several terms of this power series be given by? Sophia?
1.
Yeah? Yeah? This is fun.
Negative 28.
Good. Plus 81x to the fourth. Did we do it? Did we do it? All right. Let's go ahead and see how we did that. So again, or to our y equals, we'll enter our function in the original. And what are we entering? We're entering 1 over quantity, 3x plus 1. Yes? And we're entering the first several terms of our series. That series was 1 minus 3x plus 9x squared minus 27x cubed. All right. Uh-oh. Double x. At least it wasn't triple x. I mean, we're more mature, but come on. Plus 81 x to the fourth. Make it enough? Are we good? Let's do it. There's my original in blue, and here comes the red expansion for the first several, and don't see it, don't see it, don't see it. Ah, so look at that. Looks like it just takes off there out into the, right, infinite values forever and ever and ever. Well, you know what? Our interval of convergence that we determined algebraically was only in between negative 1/3 and positive 1/3. So we're really only looking in this little window to see how well our power series does. We know that it's going to diverge, right, as soon as we get to 1/3. And so if I were to enter things like 0.2, trace, enter, we see that the difference between my actual function values and my predicted is still just 0.02, 200ths, right? And I only went to the 4th power, not to the 6th power like we did in our original, right? And so we see that these are close values here, right? But as we get closer to 1/3, that is 0.33, you see it gets less and less of a approximate. Awesome. All right. So developing a function that represents a series is one thing. What about then determining its derivative, both in series representation and as a function? Well, the function is going to be easy. What is f prime of x in its interval of convergence? We just generated a rule for f, and it's 1/3 x plus 1. And so if f is 1/3 x plus 1, then we already have our AB rules that allow us to differentiate and get f prime. So f prime of x would simply be the derivative of this quotient, or you could do that as a power function, currently 3x plus 1 quantity to the negative 1. Either one is fine. You guys want to do quotient rule, or you guys want to do power rule? Power rule, so this is currently quantity to the negative 1, which means the derivative is current exponent negative 1 times quantity to the 1 less times the derivative of the quantity. Rewritten in preprint, I get negative 3 over 3x plus 1 squared. Yes? Okay, and so while it was easy to generate f prime using a function representation, what series does f prime represent, right? What series does f prime represent? Well, that'd be bad news if, right, we didn't realize that we could differentiate our series term by term, right? Just like we differentiate a function using our rules, we could differentiate a series term by term, which means we could use our generalized expression for the nth term and differentiate that using our rules, and then I wouldn't have to go through trying to rewrite that and make it look like 1 minus x, right? So I could figure out the substitution. That would be a lot trickier. And so let's instead go to my power series representation. F was represented by negative 3 to the n, x to the n, yes? So if this equals guess what? Its derivative, f prime of x, must be given by, hold on to your hats, this negative 3 to the n, right, is just a constant. And what's the, and so it's a constant multiplier, and so it's going to stick around for my party as a scalar multiple, just like when we did our derivative rules. And so I'm going to have a negative 3 to the n in my representation, my series representation. We preserve domain restrictions. So I'll keep my counters here, 0 to infinity. The derivative of a constant times a function is the constant. Ready? Times the derivative of a function. What do you suppose the derivative of x to the n is? That is the nth term using my generalized rule. Right? Nx to the n minus 1. Yes, this is, right, this is the derivative of my generalized term, x to the n, times my constant multiplier. So the series representation for my function that I differentiated, I can gain by differentiating my nth term general rule for the series. That's pretty sweet. All right, one more thing. I want to connect this back to what Sophia said. I want to see, right, this come full circle and see if we made any mistakes. So let's go ahead and list the first several terms of my derivative f prime. When represented as a series, the first several terms would be what? Well, the first several terms would be, let's plug in 0. Here we go. 0, so that's just 1. 0, 0, so 0 is the first one. So I don't even need to write that. When n equals 1, what happens? When n is 1, this is negative 3 times 1 is negative 3 to the times x to the 0, which is just 1. So what do we get? Negative 3. Increment my counter by 1. Now I'm up to n equals 2. When n is 2, negative 3 squared is positive 9. Times 2 is 18. X to the 2 minus 1 is 1. So that's the first. When n is 3, negative 3 times to the third is negative 27. Times 3 is negative 81. X to the... That's enough. Ready? Okay, everybody see? Negative 3 plus 18x minus 81x squared. So if we expanded and we would have gotten the derivative of this term by term would have been 0 minus 3 plus 18x minus 81x squared. By golly, ours is correct. So whether we differentiate term by term in our expansion or the nth term generalized rule like Riley did, right? Or the function f of x, right? We can generate a representation that's either that continuous function we're used to seeing or the series representation. So this is kind of a big deal, right? Being able to represent a function, a continuous function, as a sum of individual power terms, and that is the topic, right, for the first half of this unit, really is power series, and how I can use power series then to represent more important functions like the transcendental functions, okay? And so that's just a little preview, a little taste of where we're headed. All right, let's go ahead and practice another couple different situations. State the function that the given series represents and determine its interval of convergence. This time we're not given a generalized nth term. Instead, we're given an expansion. And so we've got an extra step. We have to generate the nth rule and term first on our own, and then rewrite it as a function. So this is good practice for our summation notation. I think we're going to be able to do that. We're trying to make this look like our sum from 0 to infinity of x to the n, right? And we're trying to figure out what that x is. We're trying to generalize this rule. Well, how long is the pause before it becomes awkward? I don't know. So what do you guys think? No? This will be good practice. Let's go ahead and start with the summation notation, yes? And what do you notice about my powers of x? Well, they're increasing, yes, they are increasing. And remember, we need our counter n, right, in my series notation. When I evaluate that with term numbers, n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, I need to be able to generate that power. So what must my exponent be on the x in my series representation? Must be 4. So 0, 1, 2, 3, 4. So what must my exponent be here? 4n. Beautiful. And that handles my power part entirely. But what am I still missing? Well, yes, my exponents increase, right? And they do so with the pattern that I think we've taken care of nicely. But we've got this oscillating behavior. Do you guys see that? That's kind of a pain. Well, it's okay, though, because it's every other time. And we know that negative 1, right, raised to an odd exponent will spit out a negative. And negative 1 raised to an even exponent will be positive, and so if I just make sure my exponent on a -1 is correct, then it'll generate all those signs all on its own without the works. So let's see. I'm going to go ahead and add that part in. And I want -1 to the 0 would be positive. -1 to the first, when n equals 1, would be negative. Second, positive. Third, negative. So it looks like we're set if I just do n. Yes? All right, so we check. Let's do a quick check. 0 in for n, and I get 1. X to the 0 is 1, I get 1. Well, that's good. Let's plug in 1. -1 to the first is -1, x to the fourth. That's good. Let's plug in 2. -1 to the second is +1, x to the 4 times 2 is 8. Let's plug in 3. -1 cubed is -1, x to the 4 times 3 is 12. Hey, it works. Okay, so we've generated our series representation. Our summation notation for this series. Now what are we trying to do? We're trying to figure out the function that represents. In order to do that, I need to get my substitution. So I need to see, right, what is R? What's my ratio R? What goes in for X in my generalized power function? I'm trying to get there, right? What goes in right here? What goes in for that X? What goes in for my ratio R? All right, so let's go ahead and rewrite this. So we're trying to make it look like X to the n. R to the n, something to the n. So I'm going to go ahead and rewrite this. And I'm going to rewrite it as, well, we can do the same thing we did with exponents before, right? So we can do x to the n, x to the fourth times n, we multiply exponents. So that would really be -1 times x to the fourth is negative x to the fourth all to the n. So we could regroup that, right? We can regroup that because when we take a power and we raise it to a power, what do we do with the exponents? Multiply them, and so this is really x to the fourth all to the n. And so I have -1 to the n and x to the fourth to the n. I can regroup that and rewrite it as my ratio R to the. So what do we want? I want to rewrite this as -x to the fourth. Yes? That's it. Why is that helpful? Well, because now this looks exactly like my power series, the sum from 0 to infinity of x to the n. It's just instead of x there, or r there, I have -x to the fourth. So I'm all ready for my f of x representation. I know that this is given by the function, right? This is given by the function. First term is 1 over 1 minus, instead of r, instead of x, what am I going to put? -x to the fourth. That's it. Which in turn then will be rewritten as 1 over 1 plus x to the fourth, or x to the fourth plus 1. That's pretty sweet. Okay, I know that my general power series converges when r, right, magnitude of r is less than 1. I know my general power series as a function converges when x is in between -1 and 1. This one's going to converge when -x to the fourth magnitude of is less than 1. So let's go ahead and see its interval of convergence. I'm going to go crazy and call that the IOC. Not for International Olympic Committee, but for the interval of convergence as we get closer and closer. So here we go. What do? We're going to set my substitution, -x to the fourth, magnitude of has to be less than 1 for this to converge. And I know that this is just -1 times x to the fourth. So the absolute value of -1 is just a 1 out front, which means that I just need x to the fourth to be less than 1. And the fourth root of 1 is still 1, so it looks like it preserves the same interval of convergence, -1 to 1. So it's the same as my parent power series. Cool. Can we find up front? Of course we can find f prime. We just generated a rule for f of x, and we can utilize our AB shortcut rules. Now, we got 1 over x to the 4th plus 1. Is that right? So our f prime of x will be given by the derivative of this, which again we can do power rule, and I'm going to get negative 4x cubed over quantity x to the 4th plus 1 all squared. And you can verify that with the application of the power rule with a chain. Yes? Okay. I'm really excited about our next part. What series does this represent? Can you imagine trying to rewrite that and make it look like a over 1 minus x, right, to generate the series? Well, that would kind of be a pain in the butt, right? However, that's okay because we have just generalized the nth term in summation notation. How are we going to get to, right? How are we going to get to our series representation? Let's just go back to our original nth term summation notation and differentiate it. Keeping in mind that this negative 1 to the n is just a constant multiplier. So it's going to stick around in my rule. My variable portion is just the x to the 4n. And if we had a shortcut rule to differentiate a power expression, we do, right? And it's my favorite Power Wheel song, Power Wheels. And so let's go ahead and remind ourselves what our summation notation was for the function. It was n equals 0 to infinity of negative 1 to the n x to the 4n. Is that right? Therefore, f prime of x must be represented by n equals 0 to infinity of, how are we going to do this? Well, that's just a constant multiplier, so my derivative will still have negative 1 to the end of it. Yes? And then this is going to be, what will this differentiate to? And what will that differentiate to? Riley?
Isn't it just 4x?
4nx to the 4 minus 1. That's correct. If we had more time, we would totally expand this and enter y2 and enter my derivative function, right? And set our angle of convergence negative 1 to 1 and see how well the curve matches. But we don't have more time, so we're going to keep on trucking. Thanks, Ryan. Appreciate your help. All right, let's go ahead and do a couple more and then closure. And then your assignment. So I think this is going to work out perfectly. Now let's go the other direction. So in the first several, we've given you a series representation and asked you to determine the function. Now let's start with the function and determine the series that it represents. Can we go the other way? Well, I hope so. We need to be able to rewrite this, however, like this. So we can see what to plug in for r in my series representation. Do you guys see that? So we need to be able to rewrite it and make it look more like this. So what tools do we have in our bag, comma baby? Well, it's so close, isn't it? I mean, if that were a 1 on top, we'd be done. But it's not. So what can we do when the degree of my numerator and denominator are the same?
Either multiply by 1 over x.
Oh, would that work? It might work. Oh, but it'll make a compound fraction. It'll make a fraction in the fraction. Right? In the bottom. And then if I made a common denominator, simplify to get right back here. Let's do, well, we could either add a clever 0 or something that will always work. Yes, Courtney. Oh, but I'm going to rewrite so I have dominant. I'm going to rewrite so I have negative x plus 1. Did everybody see that? So top divided by bottom. In my long division algorithm, that would be x divided by negative x plus 1. Let's focus on the dominant. So negative x times what equals x? Negative 1. So negative 1 goes there, and then you top times the side all the way through. Negative 1 times negative x plus 1 is positive x minus 1. And then what do we do? Subtract quantity. X minus x is 0. That's good. We don't have to drop off. And then plus 1. So it looks like I can rewrite my original f of x as -1 with a remainder of 1. And what was my denominator? My original denominator? Yeah, baby. Why am I so excited? I love math. Because look at 1 over 1 minus x. Don't we know what that is? Yeah, that's my parent power series, right? The sum from 0 to infinity of x to the n. So like we almost be done. Oh gosh, no we're not. I still need to write that. So this would be -1, ready? Plus the sum from n equals 0 to infinity of, and what is this? Well, this is just my regular plain Jane power series. Yes? And I'm just wondering if this will be any prettier if I do this. So I'm gonna get crazy here. I'm just gonna test and see if this will be any better. You see guys, if I put that -1 there, right, from the front, and if I expand this out, what would I get when I expand this out? 0 in for n makes my first term what? 1 plus x squared plus x cubed. Yes? And why did I do that? Well, because look, you guys see it now?
Yeah.
-1 plus 1 is 0, and so my power series is x plus x squared plus x cubed plus dot dot dot, which I don't know if that really does anything for us, but allows us to rewrite this as a single summation. I don't need that -1 out front now. I can rewrite it like this, just make sure that my counter is correct. So you can do this 2 different ways. Now it's my first term. Yeah, if I rewrite it like this, it would just be 1 here. Then it would be 1, 2, 3, 4, first term, second term, third term. So that's the easiest way to do it. What's the domain? Sorry, the interval of convergence for this? Plain Jane x for my input. Therefore, regular interval convergence versus what? -1 to 1. You guys are awesome. Oh, I feel like we're so close. So I think that we have to hold off. I think we have to hang on to that one, okay? I do. And I see myself modifying the assignment as we speak. You guys did such a good job today. So what I want you to do is go ahead and show me you get it. The series represents what function? So let's go ahead and practice with the rewrite and see what that looks like. And then what is its interval of convergence? And then we'll talk about it. And I'll pause for a minute. Okay, ladies and gentlemen, I just want to make sure that we get there. So here we go. What function is represented by the series? Well, in order to do that, I need to rewrite this so it looks like r to the n, right? Or x to the n, or blah to the n. So let's go ahead and use our properties of exponents to rewrite this. This is a lot like a to the n times b to the n, because my properties of exponents say that x to the 2n is the same as x squared to the n. And we're rewriting it like this. We see that we can join this as a product of -5x squared. That's going to be my ratio r. So this becomes, here we go, -5x squared. Right? So can I rewrite this as a function? Yes. F of x would be given by, first term 1 over 1 minus a -5x squared. Uh-oh, I'm doing that. And that would be written as 1 over 5x squared plus 1. Yes? Raise your hand if you got that already. Yes? Interval of convergence, you just set this equal less than a 1, -5 divided by 1/5, -1/5 to 1/5, -1/5 to 1/5, -1/5 to 1/5. Oh, yes.
-√1/5.
Yes.
So √5 over 5.
Okay. So what's up?